Hello, this video is for geometry, chapter 2, section 3. We are talking about conditional statements today. And a conditional statement you're probably all very familiar with, especially if you have parents, which of course all of you do. It's those if-then statements. A conditional statement is basically a statement that can be written in the if-then form, and a lot of you know that kind of thing. If you want to go to your friend's house, then you have to do your homework, or if you want to drive, then you have to have good grades, blah, blah, blah. So, today we're going to talk about if-then statements, and each conditional statement, I should say, has two parts to it, what we call a hypothesis and what we call a conclusion. So it's very important that you recognize that the hypothesis is pretty much the portion of the statement that comes after the word if. So I have highlighted the word if and then in different colors so that you do not get confused. The hypothesis does not include the word if. It is just the phrase that comes after the word if. The conclusion of the statement then would be the phrase that comes after the word then. So the word then is not part of the conclusion. Okay? So, in this case, the hypothesis of this statement, which says if you want to be a calculus student, then you must take pre-calculus. So the hypothesis is that you want to be a calculus student. And of course, all of you do. And then the conclusion is that you must take pre-calculus. All right, so I put the P and Q here in parentheses because we can oftentimes abbreviate things by using P and Q, and the P basically represents the hypothesis part of the statement, and Q represents the conclusion part of the statement. And so symbolically we can say that P implies Q. And the symbol that we use for that is this arrow here with P going to Q. And we can also demonstrate that or represent that with this Venn diagram over here, which basically when the P circle is, the P portion of the diagram is completely inside of the Q, it means that if P, then if you are inside the P circle, for example, then you're automatically inside of the Q circle, which is why it says P implies Q. All right, so that's kind of how you can model it with the Venn diagram. So we want to get to some examples here. First, I will tell you that this section can get, it's not hard, it's just that there's a lot of writing to do. They will ask you to write statements out, and you'll have to write them all out, and that's not typical of a math class. You know, usually you're just doing some simple algebra equations and that kind of thing. But in geometry, especially this chapter, this is all about logic. You will see a lot of writing and sentences, and it'll almost feel like you're in an English class. But rest assured, you're in a math class. So here we go. It says, identify the hypothesis and conclusion of each conditional statement. So what I would like to do is, we said earlier that P generally is what we use for the hypothesis. So I'm going to use P here. And here's the word if. So we said that it's the phrase that comes after the word if. So the hypothesis in this statement is the forecast is rain. Okay? And then we have, for our conclusion, we can abbreviate that with the letter Q. I don't have to write out the whole word conclusion. The conclusion is the phrase that comes after the word then. So it's, I will take an umbrella. So see, it's not hard, but it does take a little bit of time to write all that out. Okay, and then we have a part B, and they try to throw you through a loop here, because in part B it says a number is divisibly, wow, that's a really bad typo there, I'm so sorry. That should say is divisible by. Divisible, let me see if I can fix that. So sorry there. Divisible by 10. Sorry, I must have gotten ahead of myself there. Okay? So it says here, a number is divisible by 10 if its last digit is a 0. So first of all, you might be noticing that this is not in your traditional if-then format. But like I said before, the hypothesis is the phrase that comes after the word if. Also, another thing that I wanted to remind you is that the conclusion depends on the hypothesis. Okay, so that's important to keep in mind. The conclusion always depends on the hypothesis. So it says here a number is divisible by 10 if. So it being divisible depends on whether or not its last digit is a 0. So because of that, we can kind of see that this conditional is kind of written backwards. So our hypothesis is that a number has 0 as the last digit. Alrighty, so the last digit of a number is 0. That would be our hypothesis. And then our conclusion is that if that's the case, then the number should be divisible by 10. So our Q is that the number is divisible by 10. And I'll write that the right way this time. Okay? So that's how you do that. It's not really complicated, but you do have to write it all out. So there you go. We can now let you try these two. Remember, this one's in the traditional if-then format. This one's not exactly in the right if-then format, but you can figure out which depends on which, and then you can go from there. So now we have example 2, when we're talking about, again, more specifically, we already saw a little bit of that in the previous the previous example. These are not written in the if-then format, and so our job is to write them in an if-then format. So just identify the hypothesis and conclusion for each conditional statement, then write the statement in if-then form. And that's a lot to do here, so we're going to see if we can, what I'm going to do is I'm going to put P over here. And remember that when we're trying to identify hypothesis and conclusion, for the conditional, you want, because there's no if-then, you have to ask yourself which depends on which, because remember the conclusion always depends on the hypothesis. Okay, so here we have a statement: a mammal is a warm-blooded animal. Okay, so obviously you have two things going on here. You have the fact that it's a mammal, and the fact that it's warm-blooded. So either being a mammal depends on being warm-blooded, or being warm-blooded depends on being a mammal. And I think that the latter is the case. Being warm-blooded depends on you being a mammal. So my hypothesis is that you are, or an animal is a mammal. Okay? Animal is a mammal. Oops. Not having the best English writing day today. An animal is a mammal. Then my conclusion is that said mammal or animal is warm-blooded, right? So there we go. It referring back to the animal, it is warm-blooded. Okay, awesome. Now, the very last thing we have to do is, now that we know what P and Q are, it'll make it very easy to do the next part, which is to write it in if-then format, because all we have to do is go if, now I'll write it, I guess I'll just write it down here, if, and then, so if P, right, so if an animal is a mammal, then it is warm-blooded. So it makes it very easy to write the if-then statement when you first identify what the hypothesis and conclusion are. So now we'll do it again with this next example. A prism with bases that are regular polygons is a regular prism. Okay, so a prism with bases that are regular polygons is a regular prism. So being a regular prism depends on whether or not the prism has bases that are regular polygons. And so, like we said before, since the conclusion should depend on the hypothesis, then that tells us that the hypothesis is that a prism has bases that are regular polygons. So a prism has bases that are regular polygons. Okay? And then our conclusion is that if that's the case, then it is a regular prism. Alrighty? And then once we've done the identified P and Q, then we can write the conditional very easily by saying if a prism has bases that are regular polygons, I told you it was lots to write, then it is a regular prism. All right? So if a prism that has bases that are regular polygons, then it is a regular prism. Forgot my S there. All right? So now we give you a chance to do a few here. And then we're going to go to truth values. And we did some of those in the last class. So I am going to have to get this kind of out of your way here. And here we have a crazy chart. And I just wanted to give you this chart so you can kind of understand what is happening with conditionals and the truth value of conditionals. Then we have a couple of statements that I want you to write down in the next slide that are pretty important for you to understand how truth value of conditionals work. So first, I have an example conditional for you. It says, if Tom finishes his homework, then he will clean his room. And I hope that you have seen that I have tried to keep it color-coded using this bright green for the hypothesis, even in the previous slides and continuing it here, hypothesis in the green, and then the conclusion in the bright pink. And so here's our conclusion. And so then over here we have the conditional all together. Okay, so there are a couple of scenarios here about conditionals, remember, okay? So I want to kind of show you what's going on here. What if the hypothesis is true? Because, by the way, a hypothesis is just that. It's hypothetical. We don't know that it's actually going to or not going to happen. So it can be true or it can be false. Okay, the conclusion could be true or false. And then we're going to figure out, depending on which is which, how does that affect the actual conditional itself? Okay, so is this a true conditional? Well, if the hypothesis is true, which is that Tom finishes homework, and the conclusion is true, then the overall conditional is true. This would make sense. If Tom does finish his homework and he does clean his room, then obviously the conditional is true. Okay? But what about if Tom finishes his homework, but then he doesn't clean his room? Well, that makes for a false conditional. And this is actually one of the only ways, not one of the only ways, it is the only way for a conditional to be false. The only way for a conditional to be false is for it to be hypothesis true, conclusion false, then the actual conditional will be false. So here we have, if Tom does not clean his room, hence the conclusion being false, after he does finish his homework, so he did finish his homework, that hypothesis is true, then the conditional is false. Basically, he doesn't fulfill his promise of cleaning the room, and therefore it's a false conditional, okay? And then we have over here these question marks, which we're going to explain in a second. We're going to convert those to truths in a second. But here we have, what if the hypothesis is false? Then what happens? So we have two scenarios where the hypothesis is false. And I want to be very clear here. The conditional, the original conditional, only indicates what will happen if Tom does finish his homework. We don't know what happens when he doesn't finish his homework. Okay, all we know is what's supposed to happen when he does finish his homework. So he could clean his room or not clean his room if he does not finish his homework. Okay? Again, don't be very clear. The conditional only tells us what happens if he finishes his homework. If he doesn't finish his homework, we don't know what happens. Okay? So a lot of times students want to think that if he doesn't finish his homework, then he doesn't clean his room. But that isn't necessarily the case. He could choose to clean his room or not clean his room if he doesn't finish his homework. Okay, so we have these question marks here, so I'll talk about that for a little bit. Over here, we have a couple of statements. We want to summarize this for conditionals. When the hypothesis of a conditional is not met, hence it would be false, like if he didn't finish his homework, then the truth of a conditional cannot be determined. We do not know from that information whether or not he cleaned his room, because the conditional never stated what happens when the hypothesis is not met. Okay, so the first thing we have to say is that when the hypothesis of a conditional is not met, the truth of a conditional cannot be determined. Okay, that's the first part. Then secondly, when the truth of a conditional statement cannot be determined, which is what we just said in the first part, if it can't be determined, then basically it's considered to be true by default. Whoa, okay, so first we're saying that if the hypothesis is not met, that we can't determine the truth value. And if we can't determine the truth value, then it's considered to be true. Okay, so how does that work? That's what the third part is. If a statement is not false, okay, so if we say that the truth value can't be determined, then that means that it's not false. Then logic, this is where the logic kicks in, then logic dictates that it must be true. And that's what's happening in this case over here. Okay, we can't prove that it's not false, so that it must be true. Okay, so both of these guys would end up being, trues. Sorry there, got some, hold on. We want to undo that and undo that. Sorry. Okay, so what we want to do is put trues right here. Okay, so that information is summarized over here. We have a case where hypothesis true, conclusion true, conditional true. Hypothesis true, conditional false. Sorry, hypothesis true, conclusion false, conditional false. And I put this in red because this is the only way for a conditional statement to be considered false, is if the hypothesis is true and the conclusion is false. So in the case where the hypothesis is false, then by default the conditional is true. So if this is false, by default it's true. So it kind of summarizes what we just said previously about the false situation. So again, a conditional is false only when its hypothesis is true and its conclusion is false. So basically what I want you guys to think about is when you're analyzing a conditional, don't try to determine whether or not the argument makes sense to you. That is not your job. When you talk about logic, it is not your job to read the sentence to see if it makes any sense to you. Instead, what you want to analyze is the form of the argument to determine, excuse me, whether or not the conclusion follows logically from the hypothesis or not. So be very careful not to try to get too into what it's saying, and then just look for the right form that you're seeing here. Okay, so we have an example now. Determine the truth value of each conditional statement. If true, explain your reasoning, and if it's false, you want to give a counterexample. Okay, so here we go. I need to get my, sorry, I keep losing my, my strip. Okay, so here we go. So, if you divide an integer by another integer, then the result is also an integer. Okay, determine the truth value of each conditional statement. So first we want to find the hypothesis. Divide an integer by another integer. Okay? That's my hypothesis. So, my conclusion is the result is also an integer. Okay? So I'm going to use an example here. Let's see. This is totally false. I can tell you that right now. Okay? And when something is false, remember, for a conditional to be false, you have to find an example where the hypothesis is true, but the conclusion is false. So it's very easy to do. What if I pick two integers like 2 and 3? 2 is an integer. 3 is an integer. I'm dividing an integer by another integer. So this part is true. But clearly, 2/3 is a fraction. It's not an integer. Now it is true that if I take something like 10 divided by 5, that's also taking an integer and dividing it by an integer. Hence the result is a 2, and 2 is an integer. So there are some examples that will work, but it won't always work. So my job is only if it's false is to find a counterexample, and this is not a counterexample, but this is. I picked two integers, 2 and 3, I divided them, and the result was not an integer. So that's false. What about B? B says, what in the world? Okay, B says, if next month is August, then this month is July. Okay, if next month is August, so if that's true, if we say that the first part of it is true, then this month is July. Well, we know that this is a true conditional, okay? Because the first part, if this is true, then the conclusion will also be true because obviously July comes before August. So there you go. This guy would be true. So B is true. And then we have one more. Let's see. Part C. Even in the case, let's see here. If a triangle has 4 sides, then it is concave. Well, clearly, the first part of this statement is false, right? A triangle does not have 4 sides, so that's false. But remember what we said earlier with that whole conditional thing. If the hypothesis is false, then it doesn't really matter whether the conclusion is true or false. The statement overall is going to be true. The only way to have a false conditional is for it to meet the hypothesis. Okay, hypothesis true, but conclusion false. If the hypothesis is false, then by default, our conditional is going to be true. Okay, so for part C, the hypothesis is false. Since a triangle can never have 4 sides, a conditional with a false hypothesis is always true. So there we go. Now we're going to give you a chance to do a couple. Whoop, let's see if I can get that going. Okay, there we go. You'll try these two right here. And then we're going to go to this, related conditionals. All right? Related conditionals are basically a series of writing things backwards and with knots. And I don't mean knots, K-N-O-T-S, I mean knots, N-O-T. We talked about this in the last lesson. That little symbol means not. So we have 3 related conditionals. So the one in black here is just the original conditional, P implies Q. But we have 3 other types of conditionals that can stem from the regular conditional. First up, we have the converse. And as you can see in the case of the converse, the hypothesis and the conclusion switch roles. So instead of P implies Q, we have Q implies P. It's basically backwards. Okay? Then we have the inverse. Now the inverse is not backwards. It's not Q and P, it's P and Q. So it's still P, then Q, P, then Q. But the inverse puts the not in front of it. So you're going to have not P implies not Q. All right? And then you have a contrapositive. And the contrapositive is basically the whole shebang bang. It not only flips them around, it reverses the order, so the Q comes before the P, but it also negates everything. So not Q implies not P. All right, now in this whole mess, I just wanted to kind of let you guys know that a conditional and a contrapositive are always going to be what we call logically equivalent. That means that they will always have the same truth value. They'll either both be true or they'll both be false, but they're logically equivalent. They will always have the same truth value. Also, the converse and the inverse will always be logically equivalent. Okay, so That being said, if a conditional is true, okay, if the black one, if the conditional is true, the converse may or may not be true. So if the conditional is true, there's no relationship between conditional and converse. We have a relationship between converse and inverse, logically equivalent. We have a relationship between conditional and contrapositive, logically equivalent. But between conditional and converse, there's no arrows drawn to those two. Between conditional and converse, there's not necessarily a relationship. If this conditional is true, the converse doesn't necessarily have to be true. So there we go. Based on that, we have our next example here. And don't think I'm crazy. This example is actually on page 110. And I say that because when you read it, you're going to be like, what? It says, write the converse, inverse, and contrapositive of the following true statement. Then use the information at the left, hint, hint, left, what left? Right, my board doesn't have a left. So, but if you look at page 110, next to example 4, you will see a real world link with a tiger or lion picture in it. And that's what they're referring to when it says, then use the information at the left to determine whether or not each related conditional is true or false. If it's false, find a counterexample. So we have some work to do. First and foremost, I want to write this guy in the if-then format. So if, okay, I'm talking about lions are cats that can roar. So if you are a lion, and I'm guessing you're not because you're human, so we'll say if an animal is a lion, then it is a cat that can roar. Now, to be clear, this is just me taking the actual statement and making it into the if-then statement. That'll make it easier for us to write the converse, the inverse, and the contrapositive. Okay? If an animal is a lion, then it is a cat that can roar. All right? Now, based on the information at the left for this statement, based on the information at the left, which, by the way, if you don't have your book with you, I'll read it for you. It says, cats in the genus Panthera include the leopard, jaguar, lion, and tiger. These are the only cats that can roar. They cannot, however, purr. So based on this information, this statement is true. If an animal is a lion, then it is a cat that can roar because it was one of the animals that was listed in that information. So over here off to the side, I'm going to put the truth value. This is true. This is the conditional, okay? So conditional is true, all right? Now what they want me to get up here is we want the converse. Now remember, the converse just reverses the roles. So if an animal is a cat, is not a cat that can roar, right? If an animal is a cat that can roar, then it is a lion. So we want to put any knots in there. We want to reverse the roles. If an animal is a cat that can roar, if an animal is a cat that can roar, okay, so I'm taking this conclusion, a cat that can roar, and I'm putting it into the hypothesis. If an animal is a cat that can roar, then it is a lion. Yay. And now, we want to talk about the truth of this statement. If an animal is a cat that can roar, then it is a lion. That is actually false. Okay? And this is the converse. And the reason why that is false is because the hypothesis can be true if an animal is a cat that can roar, okay? But it doesn't have to be a lion. It could be one of the other names that we named. It could be a jaguar, it could be a leopard, or a tiger. Those were also listed in there. A tiger is a cat that can roar. but it is not aligned. So I have a counterexample, one where the hypothesis is true, but the conclusion is false. A tie